This lecture is going to go over how to determine empirical formulas and molecular formulas. Before you get started, make sure you have three things. You want to have a periodic table. Make sure it's one that you can easily read the masses of your elements. Also, you want to have a calculator, and you need that objective sheet to make sure that you are familiar with what you are supposed to be able to do by the end of the lecture and the practice problems. So I'm going to go over definitions first. It will be a little vague here, but as we continue to use these terms and we look at some practice problems, you'll understand what these terms mean a little bit more. So the empirical formula, we're going to associate that with being the simplest form. So if you can remember that empirical means simple, that's a really good place to start. And then the molecular formula is going to be the actual form of a compound. Some people call it the real formula. So we'll kind of see what that looks like in just a second here. But empirical is the simplest, molecular is the actual or the real formula. So there's a compound called benzene. It is made up of carbons and hydrogens, and its molecular formula, or its actual formula, is C6H6. So if someone were to see C6H6 that is familiar with chemical compounds and their formulas, they would associate C6H6 with being benzene. They're synonymous with each other. However, the empirical formula, remember that definition we just did a slide ago, it's the simplest form. So you're probably thinking, how do I make this simpler than what it already is? Well, if you divide everything by 6, we could come up with the simplest form of this compound. It's CH. So you can kind of think of it as if you're reducing fractions. If you had something like 2/4, and we could reduce that to being 1/2. It's the same thing. Same idea that we're looking at here. So another one, water. We're all very familiar with water, right? So its molecular formula is what? H2O. Hopefully we all got that right there. Now, the empirical formula is going to be the simplest form of that. Now, what you have to remember is that your subscripts in a chemical compound must be whole numbers. So is there a whole number that we can divide 2 and 1 by to make this simpler? The answer is no. We could divide everything by 1, but that's going to give us the same answer. So our empirical formula is also H2O. Now you're probably thinking, how does that happen? Why are they the same? Well, sometimes the molecular formula or the actual formula is the simplest form of that. We can't go lower than H2O, but H2O is water. So if you end up getting a molecular formula and an empirical formula that are the same in your problem, do not assume that you did it wrong because they're the same answer. This is a possibility, and it happens quite often. All right, so the steps to finding the formula. So we're going to start out doing the empirical, and then we'll move to the molecular. But you're still going to have to go through these steps for both of them. So step number 1 is converting grams into moles. So you know how to do that. You've already done your previous quizzes. If you're given X number of moles of carbon, divide it by your molar mass, and you'll be left with the moles, making sure our units cancel. However, sometimes you are going to be given a percentage. And what we're going to do when we're given a percentage is we are going to assume that we have 100 grams of whatever we're looking at. So if it says that we have 29% oxygen, I'm going to assume that we have 100 grams, which means that 29% of 100 would be 29 grams. So if you are given a percentage, assume 100 grams and then convert those percentages into grams. Not a difficult thing here, okay? Step 2, you're going to divide all moles by the lowest number of moles. Now remember, back here in step 1, we're going to convert those grams to moles. So we're not just going to stop here at the 29 grams of oxygen. We're going to convert it into moles. 16.0 grams per 1 mole. And then let's do the math on that. Equals 1.813 moles. Okay. Now, your formula is not only going to have oxygen, it's going to have oxygen and maybe some carbon, maybe some nitrogen, some hydrogen. You're going to find that mole for all of them, the number of moles for each one, and you're going to divide each of them by the lowest number of moles per whichever one. So if you had something else in your formula that had 2.6 moles and your oxygen had 1.83, this would be your lowest number, so you would divide everything by 1.813. We're going to do an example here in just a second, okay, so stay with me. Step number 3 is whole numbers are going to become subscripts, and non-whole numbers must be multiplied to make a whole number. So if you end up with a number after you find this mole ratio here, like 2.5, we're going to multiply that by 2 to make it 5. So just a key here is that you need whole numbers. So keep these steps close by. We're going to go through and I'm going to show you what each of them looks like. All right, problem number 1. A solution is found to contain 89.14% gold and 10.80% oxygen. What is the empirical formula? Now remember what I said, step 1 was converting your grams into moles. Do I have grams here? No, I only have percentages. But what did we say about percentages? We are going to assume that we have 100 grams, so we're going to make those grams into a percent. So instead of being 89.14% gold, we have 89.14 grams of gold. And then we're going to do the same thing with the oxygen. Convert those percentages into grams. Now, do I want grams? No, I want moles. So 89.14 grams of gold. Now to find that, we're going to have to use our molar mass, 196.97 grams. 1 mole. You should be doing this with me, not just watching, because you want to make sure that you're getting the same answers. If I multiply this out, I get 0.45 moles. Now let's do the same thing with the oxygen. 16 grams, 1 mole, going to give me 0.675 moles. So that's step 1. Step 2, if you remember, is to divide by the lowest mole number. So what we're comparing is this number, the 0.45, with the 0.675. Which one's smaller? The 0.45. So we're going to divide both values by that. Now, 0.45 divided by 0.45 equals 1. 0.675 divided by 0.45 equals 1.5. Now step 3 says that my whole numbers are going to become my subscripts. But we have a problem. This isn't a whole number. So what do I have to do if it's not a whole number? I'm going to have to multiply to make it a whole number. How do I make 1.5 into a whole number? I have to multiply. If I multiply it by 1, I get 1.5. If I multiply it by 2, I get 3. 3 is a whole number, so I'll take it. I'm going to multiply this by 2 to give me 3. Now here's the thing that I see happen a lot, is we forget this step here. If I multiply my oxygen by 2, I must multiply my gold by 2. So I'm going to multiply this by 2 to get 1 times 2 is 2. Now I have two numbers that are in whole number form, okay. And what happens to these numbers, looking at the last step? They become your subscripts. So I have AU2, O3. That came here, and that came here. So this is my empirical formula for this solution. So when we're doing this, making sure that we are converting our grams into moles, step 1. Now you have this lowest number of moles. You got your moles from one of these two. Divide by the lowest. So we picked 0.45, 0.45, and that gave us 1 and 1.5. The 1.5 was not a whole number. We need for these to be whole numbers because they become our subscripts. So to make 1.5 into a whole number, I have to multiply it by 2. Anything you multiply, you have to multiply everything else in the problem. So I multiplied my gold by 2 as well, and those numbers became my subscripts to give me AU2O3. Alright, at this point, if you want to go through and just practice empirical formulas, that's fine. If you want to continue watching and watch molecular at the same time, that's fine as well. Whatever works for you. But you are always going to really have, this empirical is always going to be step 1, so you kind of want to make sure you have that under control before you start doing all the problems with molecular. Alright, next problem. The molar mass of nicotine is 162.1 grams per mole. It contains 74% carbon, 8.7% hydrogen, and 17.3% nitrogen. Determine the empirical and the molecular formula. Now, in order to find the molecular formula, you must find the empirical formula first. So we're going to have to do the empirical formula, which is what we just did, before we can even think about finding the molecular. So I have 74% carbon, 8.7% hydrogen, 17.3% nitrogen. I have to convert those grams into moles. But those aren't even grams, right? So I'm going to assume 100 grams. 74% carbon is going to become 74 grams of carbon. 8.7% hydrogen is going to become 8.7 grams. 17.3 nitrogen is going to become 17.3 grams of nitrogen. Alright, so step 2 is converting those grams into moles. So this is 12.01 grams, 1 mole. Go ahead and do these with me. Go ahead, pause it. See if you're getting the same numbers as me. So for carbon, we should have got 6.16 moles of carbon, 8.6 moles of hydrogen, 1.23 moles of N. So now I have my moles of everything. Once I have my moles, I need to divide by the lowest number. Pause again, divide by your lowest, and come back and see what you got. Okay, so we should have got divided everything by this 1.23. That's our magic low number there. So we divided our carbon by the 1.23, our hydrogen by the 1.23, and then that nitrogen as well. So we get 5 for the carbon, 7 for the hydrogen, and 1 for the nitrogen. So if we're going to write that out, C5, H7, N, and we don't, if you have no subscript, you just assume that it's 1. Now it's important for you to keep track and keep your stuff organized, because it would have been very easy for me to have written this like this. If I would not have known which ratio matched up with which element, okay? So please, 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 please make sure that your work is organized. It also allows me, when checking and grading your stuff, to see your thought process and to see what your organization is. If I can't figure out what you were doing, it's very hard for me to help you, and it's hard for me to give you partial credit if I can't see, oh, did you make a simple math mistake, or did you mess up completely? So keep your stuff organized. It's going to help you in the long run. So this right here, the C5H7N, is our empirical formula. So now we've done 2 with the empirical. So now let's go on. Remember back in the problem, it asked us to also find the molecular. So in the problem, it gave us the molar mass of nicotine as being 162.1 grams per mole. I'm going to write the molecular back, or the empirical back up here so we can see it. Now we haven't used that number yet. Whenever you are given the molar mass of the compound, you are not going to use that until you're finding the empirical. Do not use this number. We didn't use it at all for the empirical. You are only going to use that for the molecular. So make sure that you are not using this molar mass number until you get to the end. So we're given that in the problem. The second thing we have to do is find our molar mass of our empirical formula. So remember, this is our empirical formula. Finding the molar mass should be something that becomes very easy to you now. So we'll take 5 times 12.01. That comes from the carbon. We're going to add that to 7 times 1.01. That comes from my hydrogen. And then we're going to do 1 times 14.01, and that comes from my nitrogen. Okay. So if we multiply out, we divide, or we add all those together, we should get 81.13 grams per mole for this compound right here, the C5H7N, the empirical formula. Okay, now we have 2 numbers. What do we do with them? You're going to take your molar mass and you're going to divide it by your empirical. So 162.1 grams per mole divided by 81.13. Go ahead and do that math. And you should get 1.998, then a bunch of numbers after that. We're going to round that number to 2. All right, so what's that mean? What's this 2 mean? That 2, if you're looking at this, pay close attention to your units. If I'm dividing these, my grams per mole are going to cancel out. So I'm just left with a value. We're going to use this 2 as a multiplier. This is the ratio between your empirical formula and your molecular formula. So I'm going to multiply my empirical by this new multiplier that I have, this 2. So I'm going to take everything in my empirical and I'm going to multiply it by 2. So instead of having 5 C's, I'm going to have 10. Instead of having 7 H's, I'm going to have 14. Instead of having 1 N, I'm going to have 2. Now this is your molecular formula. Now, one thing to keep in mind, and this is what you just noted here, if I have a number like 1.986, I'm going to just assume that to be 2. If you have 0 or 1.024, we're going to assume that to be 1. Now, the more decimals you go out when you're finding that mole ratio at the beginning, the closer your numbers are going to be whole numbers, okay? So don't stop at 1 digit behind the decimal. Good rule of thumb for empirical and molecular formulas is to go 3 to 4 decimals out. It's just going to make things a lot smoother, make your numbers a lot more tighter to those whole numbers. So go ahead, work through the empirical ones first, check your answers, and then we'll come back, look at your moleculars, and let me know if you have any questions.